3, 2, 1. Alright, so plot for today. We introduced the concept of eigenvalues last time, and today we will focus in on eigenvalues and eigenvectors for matrices specifically. So recall that an eigenvalue for a linear operator is a scalar lambda, such that there is a non-zero element u of v, so that t of u is equal to lambda of u. So in other words, the action of the linear operator t on the vector u is to simply scale it by the prescribed value. All right, and again, we stress that you need non-zero here in order for this to be a meaningful definition, because otherwise everything would count as an eigenvalue, since t of 0 is 0 for any linear mapping. All right, and associated to each scalar lambda is the eigenspace, the set of all possible vectors that satisfy the equation, and the elements of these are all called eigenvectors. Now note here that this is in fact a subspace, meaning that 0 is in there, because again, 0 would satisfy this equation, regardless of what lambda is. However, the requirement to be a value is to ensure a non-zero, so that not only is this a subspace, but it is a non-trivial subspace. Good stuff. All right, and we talked about the connection of eigenspaces to a very famous unsolved math problem called the invariant subspace problem. So that was a fun time. So as of this recording, still unsolved, even though PerInflow has claimed a couple of solutions that apparently not everybody fully believes right now. But maybe I'll be proven wrong in the future. All right. So, the goal for today, so we talked about these for linear operators, we gave examples for matrices, and we also looked at some non-matrix linear operators, some linear operators in infinite dimensional spaces. But today we want to hone in on what happens with matrices, because some magic happens. Alright, so eigenvalues lambda and associated eigenvectors v will satisfy this equation, and at first glance, this equation, au is equal to lambda v, is seemingly shouldn't have an answer, right? It's one equation with two unknown quantities, lambda and u. However, this is where the non-zero thing is really going to kick in, because in order for lambda to be an eigenvalue of the matrix, it's going to have to be that this determinant right here is equal to 0. So let's see why. All right, well, suppose that lambda is indeed an eigenvalue of our matrix. All right, well, then we know that this equation has to hold for a non-zero vector v. All right, again, by definition, there is a non-zero vector that will work. Well, if I kick in the math lizard brain, subtract this over, and factor out v, I now have this matrix multiplying a non-zero vector then gives me 0. So in other words, my matrix has a non-trivial element in its null space, and thus it can't be invertible, and thus its determinant must equal 0. So note there, right? That was a quick little couple of jumps of logic, right? Multiply by this element gives me 0. That means we're in the null space. Non-zero things in the null space mean we're not invertible. Non-invertibility gives me 0 determinant. There was a lot built in there, right? And let's really appreciate here towards the end of the semester all of the machinery and logic and mathematics we had to build up to get there, right? Recognizing that non-zero things in the null space, ensuring the matrix can't possibly be invertible, right? Which we proved because we proved invertibility was equivalent to your columns being linearly independent. And linear independence of columns can only happen if your null space is trivial. And then verifying that the determinant, the magic number associated with a matrix, so again, the determinant being the unique row linear alternating mapping that sends the identity to 1, that mapping being able to detect invertibility by outputting non-zero elements, non-zero output. Right, so in this just quick little hop, skip, and jump, there is a lot of math built into that, so let's really just take a moment to appreciate that. Pause the video and really think about what you did. All right. Okay, and now that we're back, let's do it. Note it's an if and only if, which means that I have to show this implies that, and backwards. But this is a good kind of if and only if because this piece right here, just read the previous proof backwards. If that's zero, this matrix is non-invertible, so there's something non-zero in its null space, and then solving that equation gives me that lambda is indeed an eigenvalue. All right, cool. All right, so what we've now demonstrated is that finding the eigenvalues for a matrix means that I want to figure out when this equation is equal to 0. All right, now this is called the characteristic equation. It's a very famous equation, and what's even more famous about it is that it is indeed a polynomial. And we are not going to prove this. There are a few ways of getting to this proof. But I'll leave it to you to sort it out if you really want to. There's a recursive way of proving it. There's a direct way of getting it. We're just not going to work out the details of the proof here. Just trust me, bro. It's a polynomial, and the polynomial will always look like this. So the leading coefficient is always a plus or minus 1, depending on the size of your matrix. So note, again, all these matrices need to be square because we're talking linear operators. All right, and the other coefficients, there's actually formulas that are known for all of these. And outside of C1, the coefficient on the n-1 term, and Cn, those formulas are just, they're something. Go ahead and look them up if you're really interested. But the coefficient formulas for the coefficients are known. But outside of the C1 and the Cn, they're disgusting. So C1 is the trace of the matrix, and let your mind float back. We talked about the trace. That is the sum of the diagonal entries. And the Cn term is always the determinant. And note because I factored out this minus 1 to the end, there's this minus 1 to the end that will show up here as well. Note, if you plug in 0 here, you'll get the determinant of the matrix. So this constant term of the polynomial must always, in fact, be the determinant. All right, and this polynomial is called the characteristic polynomial, and we will basically only worry about the case of 2 by 2s, and note that following that formula means that the characteristic polynomial of any 2 by 2 is the trace, is t squared minus the trace times t, plus the determinant of the matrix. Cool. All right, and if you want to, you can actually work out a formula for the characteristic polynomial of a 3 by 3. It'll be negative t cubed plus the trace times t squared plus this mystery term times t plus the determinant of a. That mystery term is kind of interesting, so if you really want to sit down and calculate it out, go ahead, but we're not going to get too sweaty about it. All right, now that we've established how to compute eigenvalues, note that once you have your values, then your vectors can be found by solving that equation. Since you will know A and you'll know lambda, that is just solve that. Let's go ahead and actually do that. All right, so here's an example, 2, negative 1, 0, 3. Now by our formula here, we just take the trace and the determinant of the matrix and set it up and factor it, and we're good. Note that, again, if you wanted to, you could also directly compute the formula for the polynomial by subtracting t off the diagonal and taking the determinant, and you'll arrive at the same sort of formula. All right, nice. So the eigenvalues now we know are 2 and 3, so let's talk about how you find the vectors for such things. Well, for lambda equals 2, you would be solving AV is equal to 2V, so subtract this over, and that means you're subtracting 2 off the diagonal, and now you're trying to find the vectors v that would satisfy this matrix equation. And from this we see that v2 is 0, and so v is every scalar multiple of the vector 1, 0. So in other words, the eigenspace for lambda equals 2, E2, is the set of all multiples of the vector 1, 0. Cool. And you can do the same thing for 3, and have fun, and on the homework I'll make you do this and compute some eigenvalues and eigenvectors. Okay, and I've also given you a fun problem to directly work with the equation. All right, so hey, there you go. That's the basics of eigenvalues, eigenvectors. This is how you compute them, and great. That's what they are for matrices. Now note, for matrices, there's only ever finitely many eigenvalues, right? Because this is always a polynomial, and the roots of this are the eigenvalues. That means every matrix has, at most, finitely many. But we know something about polynomials. Since it's a order n polynomial, it has at most n roots. That could be complex, potentially. We're not going to worry about that case, though. We're going to primarily focus on the real case. But it's possible your eigenvalue appears multiple times as a root. And what we want to do to finish off today is to actually talk about that number, because that number has a name, and that number turns out to have a pretty neat connection to the dimension of the eigenspace. All right, but in order to properly get there, right, what do we need? All right, well, it turns out we're going to need this concept of similarity, and this is going to be kind of at first just a, yeah, sure, that's an equation you can form, but I can't even begin to explain to you how, like, essential this is. This just general algebraic construct of taking an element, multiplying on the right by another element, and multiplying on the left by its inverse. Like, this is such a move. And when you take Math 3010, abstract algebra, you're going to see that you can't even begin to comprehend how powerful of an algebraic technique this is. Right, but at first glance, it looks very much just like a, yeah, sure, you can formulate this. All right, but as we are going to see here, this trick of similarity for matrices is, oh boy, is this going to be a good one. All right, so first off, we'll prove that if we've got two similar matrices, they in fact have not only the same eigenvalues, but will in fact have the same characteristic polynomial. And why is this true? Well, by hypothesis, we have an invertible matrix P, so that B is equal to P inverse AP. All right, I'm claiming B and A have the same characteristic polynomial, which means I need to show that det of B minus Ti is det of A minus Ti. And what the trickery is going to be here is that, well, B is P inverse AP. The identity matrix is P inverse times P. And hey, we can factor out P inverse on the left and P on the right. And then now, as we mentioned, the determinant is multiplicative, meaning that if you feed it a product, you get the product of the determinants. The x of the y is the y of the x, our favorite mathematical phrase, and as we mentioned, the fact that the determinant is multiplicative, quote from Dr. Weber, this is like the most important thing, and here we see it in action because now this determinant splits up like that. These are now numbers, so multiplication is commutative, so I can move this one over here. And then we can reconstitute that product, and that gives me the determinant of the identity, which we know is equal to 1. Okay. Note, incidentally here, we've now verified that if you have an invertible matrix, its determinant of its inverse is 1 over the determinant of the original. Ooh, pretty cool. All right, and hey, there we go. We've now verified that similar matrices have the same characteristic polynomial. All right, so like I said, similarity at first glance is just a, yeah, sure, you can formulate this algebraic expression. We've now seen that it's got a little bit of power, because if matrices are similar, then they have the same characteristic polynomial. But, big whoop, right? Okay, great. Again, why would I care about this? This just seems like a convenient thing. All right, well, now for the star of today's show. So as mentioned, we know that the characteristic polynomial is going to give us our eigenvalues. And the roots of this polynomial, well, roots can appear multiple times in a polynomial. All right, so given a matrix and an eigenvalue lambda, we define two kinds of multiplicity associated with lambda. One is the geometric multiplicity, which is the dimension of its eigenspace. So, right, we know that your eigenspace is non-trivial, so it's going to have a geometric multiplicity of at least 1, and since E lambda lives in Rn, it is at most n, so the geometric multiplicity is some number between 1 and n. The algebraic multiplicity is the largest power of T minus lambda k that would appear in the characteristic polynomial. So the number of times lambda shows up as a root of the polynomial. Right, we know roots for polynomials, they can appear more than once. So right, you can pull out a pretty big power. And let's now look at a matrix with a eigenvalue with a algebraic multiplicity of more than 1. So note that the previous example we looked at, 2 and 3 have algebraic multiplicities of 1. E2 has a geometric multiplicity of 1, since the dimension of this is 1. You can also verify that 3 has a dimension, a geometric multiplicity of 1. The associated eigenspace is at most one-dimensional. All right, let's look at another example where algebraic multiplicity is a little bit bigger than 1. So here it is, the worst matrix of all time, 1, 1, 0, 1, and I'm not joking. This matrix ruins a lot of reasonable sounding theorems. And if you want a matrix to really screw up something, you look at this one. This one, I'm like not joking. So when I took linear algebra way back in the day with good old Professor Fulton, he made a big deal about this matrix. He was always like, "This matrix sucks." He would never say that, but that's what he meant. Right, and one of the reasons this matrix is a bit of a bastard is that its eigenvalue, it has an eigenvalue of 1. The algebraic multiplicity is in fact 2, because the characteristic polynomial is t minus 1 quantity squared. So its algebraic multiplicity is 2, the only eigenvalue you can ever find is 1, but the eigenspace associated with this is also going to be just one-dimensional, right? It's pretty easy to verify that all the eigenvectors associated with 1 are just going to satisfy that. So what we found here is that I have this matrix with an eigenvalue of 1, and it appeared twice. However, its eigenspace only is one-dimensional. And as we are going to see in a little bit, so in the next lecture, so next time we have a problem session, then we'll talk about it, we're going to want to have n linearly independent eigenvectors. If I have an n by n matrix, as we're going to see, I really want n linearly independent eigenvectors. So, in other words, I always want it to be the case that the algebraic multiplicity and the geometric multiplicity line up with each other. But here we see they don't. It's possible that you appear as a root multiple times, but each time that eigenvalue appeared, the eigenspace does not match the same number. So, as we're going to see next time, it's going to be very important to have enough eigenvectors. If you have enough linearly independent eigenvectors, something magical happens with our matrix. Alright, but here we see bad news. Sometimes that just does not happen. Alright, well, it'd be great if I had some connection between these two numbers. And indeed there is. If I have a matrix, a eigenvalue, with geometric multiplicity p and algebraic multiplicity q, then it turns out that the geometric multiplicity never exceeds the algebraic. So good news, if your eigenvalue only ever appears once, this guarantees that the geometric multiplicity would have to be 1, and so a eigenvalue that appears by itself would only ever have a one-dimensional eigenspace. So the only way you could have a two-dimensional eigenspace is if your eigenvalue appears twice. It can appear more times, but it has to appear at least twice. Yeah. So, speaking of good old Professor Fulton, when I was taking linear algebra, a bazillion years ago, he claimed this result. He put it on the board, right? He went for this little matrix example, and he went, all right, and this is always true. You can always prove the geometric multiplicity never exceeds the algebraic. And then he followed up with and I'm not going to prove this, and he said something to the effect of like, "Oh, I've never seen a proof of this that I liked," or something like that. He made a deal of the proof of this being like very difficult or obtuse or something, just like a proof that wasn't worth our time. Very similar to what I just did up here with the actual polynomial. I was like, yeah, this just isn't worth our time. This is true. Moving on. And he did that for this. And so for this fact, this proposition right down here, he made that claim, and I always, I took that to heart, and, when I started teaching mathematics, then I had to, I copied my heroes, I stood on the shoulders of giants, and I always would verbatim repeat this and go like, oh yeah, this is like the worst thing ever, the proof of this is insane. Right, and I've never ever sat down and tried to prove it, even though he said it was a bad proof. I just took him, well, Professor Fulton says it's bad is bad. So, I just left it. And so if you've taken differential equations, you know that this pops up when we have a repeated eigenvalue and you want to get your two linearly independent solutions. Well, linearly independent solutions come from linearly independent eigenvectors, and so if you don't have enough, what do? Oh, there you go. So we talk about a diffie and one semester I was making some videos for differential equations, and I go on my little rant here of like, oh, the proof of this is impossible. And as always, whenever you make a claim on the internet, somebody's going to show up and tell you how wrong you are. So, right, if you ever want the correct answer to something, purposely post the wrong answer. And somebody jumped in the comments and went, actually, it's really easy to prove this, and they outlined a proof of it. And I read that little outline, and I went, wait a minute, yeah, that's a really easy proof. And then I thought about it more, and I went, wait a minute, not only is that a really easy proof, the proof of that really kind of explains why you care about similar matrices, and it sets the stage up for diagonalization, which is going to be our next topic. And so then my brain, like I started losing it, and I'm like, what was Professor Fulton going on? It's like, this is the best proof to do, especially right now. It really justifies why similarity is such a useful technique, and it's also going to sort of reveal, like, ooh, hey, diagonalization's coming up. So it's like, it baffled me when I realized it. So let's do the proof of this now, and we're going to see why similarity is so powerful, and we're going to set the stage for something called diagonalization. All right, and that'll be our lecture for today. Okay, so what's the deal? All right, so we've got P as the geometric multiplicity, so you have a basis for your eigenspace. There it is. All right, and guess what we can do with bases? As we've mentioned, you can extend them to bases for the entire vector space you live in. So let's extend this to a basis for all of our n. All right, and then I'm going to make a matrix P whose columns are these basis elements. Those are linearly independent, so I have an invertible matrix. And so now let me make a matrix B that is similar to A. And let's go ahead and look at what B needs to look like. Because note, the first P vectors of B are eigenvectors associated with A. So A times these VKs up to P are going to give me lambda. So if I look at the kth column of B, where we're looking at the kth column from 1 to P, note that B is equal to this. Then we're multiplying P by the standard unit vector EK, which means that the column of that is what we'll get, but the column of that by construction is this eigenvector. And hey, that means we then get our lambda here, which we can then pull out. All right, but now let's talk about what P inverse VK would need to look like. Well, VK is the kth column of P, and we know that's P times the standard unit vector like that. So P inverse times that will give me the identity, and thus give me the standard unit vector EK. So in other words, I've demonstrated that the matrix B, the first P columns of it, are just all scalar multiples of the standard unit vectors. So that means when I look at the matrix B minus T times I, so the matrix you would look at to produce the characteristic polynomial, the first column is just lambda minus T and then a bunch of zeros below it. The second column is 0, lambda minus T, bunch of zeros below, up until the Pth column, where you have zeros, and then in the PP entry, lambda minus T. I definitely didn't pick P to make that joke right there. And a bunch of zeros below it. And then after that, in the P plus 1 column, there'll be some entries. It doesn't matter what the hell they are, but there's entries out there. And note on the rest of those diagonals we're subtracting T. But note something about this particular matrix. What happens when you take the determinant of this? Well, by cofactor expansion, here, because of all of the zeros present, when you cofactor expand, this here will isolate this term, but then a bunch of zeros will knock out everything else. And then as you march down, doing your other cofactor expansions, you'll pick up a lambda minus T term as well, and the zeros around it are going to then ensure that, all right, well, no other things are going to pop up. Right, and you'll march all the way down, and you're going to pick up a lambda minus T P times. In other words, the characteristic polynomial is a lambda minus T to the Pth power of multiplying some other polynomial P of T. Right, so when you compute the determinant of this, right, and do your cofactor expansion, the placement of all of those zeros are going to ensure that, a bunch of things knock out, and you'll just isolate each one of these. All right. So then we have that the determinant of b minus ti is equal to that. But that means, since a and b are similar, they have the same characteristic polynomial, which means the characteristic polynomial of a minus ti is lambda minus t to the p times that, which means that the geometric multiplicity of lambda is at least p. Remember, the algebraic multiplicity is the highest power that would appear here. P appears, and maybe there's some more factors that pop out of p. The polynomial, I don't care. All right, polynomial. What am I? Polynomial. Yeah, whatever. It's fine. Anyway, so it's possible more pop up, but in other words, we know that at least p show up, which means that the algebraic multiplicity is at least p, if not bigger, and thus the proof is over. Cool, there we go. So there we see the power of similarity, matrices having the same characteristic polynomial, helping me out, helping me go like, hey, I was working with eigenvalues for this matrix A, but by similarity I can move over to this matrix B. And note, the matrix B that I picked is rigged so that, hey, it looks really nice. There's a lot of zeros. And note, hidden in the proof here is the following. If I knew that E lambda, if I knew this was equal to n, that would mean that my matrix B that I arrived at just has a bunch of eigenvalues on the diagonal and zeros everywhere else. Ooh, isn't that magical? Right, and similarly, maybe if note that all of these were for a single eigenvalue lambda. What happens if I had, v1 to vn, but each v was associated with with its own eigenvalue, lambda? Okay, well then I would still be able to pull off that diagonal thing. Ooh. Man, it'd probably be really great if I could, diagonalize a matrix or like that. Oh boy, I wonder if that's what we'll be talking about next time. All right, that's it for today. See you next time.